everybody knows that if I'm not near a magnet, if I'm holding a compass has a needle that we represent, one end as north and one end as south, right? So the north end should point to the north, right? Now, that means the unmarked end in this particular compass, it's the green end. There's a green tip on it. Everybody see the green tip?
Yeah.
So it's pointing north, and north is that direction. Now, is it pointing to true north, or is it pointing to magnetic north? Magnetic north. So this particular line is aligning with the magnetic field. If I set it down, it may even be affected a little bit by that magnet. I should want to go that direction. And that's provided that our far away from it as I can. As long as it's free floating. Yeah, it gets on up. It's on up.
It's funny in it. No.
See the red?
Yeah.
The red pointing that direction. So what happens whenever you bring a compass close to a magnet? So right now the north end is pointing that way to the north. What happens to it?
It points to the magnet.
It will start to be affected by it, right? So it should start to actually move around, see? So the south end is being pointed to the
north,
and the north end will be
south.
to the south. See that?
Opposite attract.
Why does that occur? Sorry about that. So we have that, and we move it to the other end, and it flips. So right there, we've actually seen a polar reversal, and this actually occurs on Earth. We have magnetic reversals. We have magnetic reversals that occur around the Earth, where actually our North Pole will become our South Pole. So we have these things called magnetic strips, iron strips, that are on the ocean floor, and they can be hundreds of miles long and miles wide, but they actually are the lining up of the particular atoms inside those iron fields. The domains in those fields will line up, and they line up pointing north and south. But over time, due to convection cells on the planet, they will flip. And I'll talk to you about convection cells in a little while. But as you can see, opposites attract, right? And likes repel. So if I have the red arrow, which is the north pointing tip, should technically point to what?
No.
See the North Pole? That's right. It should point to the so my north end of my compass should be pointing to. It is pointing to the North Pole, but what does that tell you that the actual polarity for that North Pole really is? If this were positive, the North Pole would be a negative. So the north end of this is it's pointing to the North Pole. It's really the South Pole of our planet's magnetic field. Okay, but we call it the North Pole because it's in the north. All right. But technically, that's a common misnomer as well, is the north end of the compass points to the North Pole, but it's actually the South Pole of our magnetic field. That means the South Pole is our North Pole of our magnetic field, because the South Pole would be pointing to the North Pole of a magnet, right? So let's watch it. South Pole points to the north, North Pole points to the south. Okay? I'll take it back. Now, what happens whenever I move a compass around this? You see how the arrows are moving? See them?
Mm-hmm.
So, could you plot if I had you put a piece of paper down on the ground underneath this? If you put a compass around and drew the line, saying the arrow's going that way to the north, and move it, the arrow's going that way, and drew it like that, arrow's going that way, you could actually plot the magnetic field around a compass. Does that make sense?
Mm-hmm.
So this is something I want you to actually do, and take you a couple of minutes to do it, each of you. Just do like this, and you can break it into groups and submit the same paper in your groups if you want. That will make it easier for you. But you just take a piece of paper, draw the actual direction the compass is pointing. See, right now it's pointing that way. And then it's pointing kind of that way. And then move it out. Move it out a little bit. See what the fields are doing out here. Okay? And it constantly moves. Now, we can see the magnetic field. It's an invisible field, right? It's not, this is iron filings. But if I put this powder on here, I can see where the magnetic fields are at. You'll see that?
Yeah.
You see how all right, do you see how we have lines that are starting to form? See them? See the lines that are spreading out, coming out like that? And that's where each one of those actual iron filings are starting to line up according to their fields. So they're actually north and south poles on each one of those particular iron particles that we have in this iron dust. And you can see that they're grouping around the North Pole and the South Poles. You see it? See it grouping in those poles? Yeah. And then it's actually having some change going on in the center, right? Yeah. You would expect that to happen, right? Yeah. Why would you expect there to be a grouping right here in the center?
Because it's in between those.
That's in between poles. If I broke that magnet right there in half, what would I get? If I broke it into two, if I just cut it right there in the middle and move the magnets out, if this is the South Pole and that's the North Pole, if I broke it in half, where would I pull this piece over here? Where would I have a North Pole at?
On the other.
I would have a South Pole here and a North Pole, a South Pole and a North Pole, right? Yeah. So if you break it, that's what happens. You create a new magnet when you do that. And it actually has a polar end again. It just polarizes. Now, there was a famous, so what's going on here are there's these little domains inside that little particle. We can zoom in on this little particle right there. Inside that particle would be a domain. That domain would have a positive end and a negative end. And it's basically an area, okay? So as an area, if they're not lined up, if they're all random, if the North Pole's facing this way and the South Pole's this way, the North Pole's this way, that means that particular metal doesn't have a magnetic property. It means it's not going to line up with the magnetic field. So there are metals that don't do that. So iron, cobalt, nickel, anything that contains those will have domains that line up according to the magnetic field. What about a piece of plastic? Plastic has random domains that are not lined up. It's not magnetic. Piece of glass, they're random. If I pull a magnet up to here, it's not going to attract to the glass. It will attract to the magnet. My iron filing inside of here because their domains are not random. They are specifically, as a majority, lined up in a certain direction. That allows the magnet to be created. All right? So, now that you've seen this, and now that you've seen the lining up of this particular compass as we move it around, you should be able to answer all those questions on that first lap. Okay? So let's split up. Let's do that. Let's hit pause on this. You already did it.